We've talked about the electric field, what it is, and what it looks like. Now let's talk about calculating it. If we think about the electric field due to a point charge, the force was kqq over r squared, but we're going to divide by the q of the object, so that's going to take out one of the q's and leave only the charge of the source. The field lines are going to point, or the field vectors are going to point away if the charge is positive and toward if the charge is negative. Because again, we're thinking of a positive touch charge determining the direction. So let's just look at this one right here. So we have a coordinate system and a proton in the center, and then half an angstrom away, we have where we want to calculate the electric field. And so we have k q over r squared is equal to 8.99 in meters squared over coulombs squared times charge 8.60 times 10 to the minus 19 coulombs, all over 0.5 times 10 to the minus 10 meters squared. Then we come up with the quantity 8.99 e. Oh, I forgot to write down the 10 to the 9 right there, times 1.6 e to the minus 19 divided by 0.5 e to the minus 10 squared, and we're going to get what looks to be a very large number, 5.75 times 10 to the 11th newtons per coulomb. Electric fields tend to be very large numbers, whereas forces can be much smaller, at least when we're talking about atomic types of electric fields. Let's look at an example where we have the electric field due to more than one charge. So we will use simple numbers, not realistic numbers, but simple ones. We'll say that this is 2 coulombs and this is negative 1 coulomb. We'll say that this is 1 centimeter, and then at a distance of another centimeter, we have the point where we want to find the electric field. Okay, so we are going to separately calculate the electric field due to the positive charge and negative charge, and then add them as vectors. So the overall electric field is going to be a right direction. So make sure we have our coordinate system, right? So a right direction, k q1 over r squared, minus, we could write it this k q2 over r2 squared. So we could write this as 8.99 times 10 to the 9 Newton meters squared per coulomb squared times, we have 2 coulombs over, this distance is 0.02 meters squared, and then we're going to subtract 1 coulomb over 0.01 meters squared. And the overall result is 8.99 e to the 9 times 2 over 0.02 squared minus 1 over 0.01 squared. And the overall result is the magnitude. Well, if we think of this as a vector, we have a negative 4.50 times 10 to the 13 newtons per coulomb. So it is pointing to the left with that magnitude. the last thing that we should look at is reversing this process, right? So we talked about how electric fields were how we abstracted the force away from the agent, and then we talked about how to calculate that field with an agent. Now that we have the field, let's see how we can actually apply it to an object that's going to feel that field and actually get a force off of it. So we've figured out an E, or someone's told us an E. Somehow we have an E. And now there's an object, Q, that's in that field, and it's going to feel the force due to that. We just multiply Q times E, and that's going to be the vector of the force. So let's say that we have an electric field. In this case, the Earth, you know about the Earth's magnetic field, but there's actually also an electric field. At every point in the Earth, it points downward with this magnitude, 110 newtons per coulomb. And we want to put a single electron in that electric field and figure out the force. So this is what that looks like. There's the E field. So first of all, let's find the magnitude of the force. And so that's going to be 1.60 times 10 to the minus 19 coulombs times 110 newtons per coulomb. And so I should be able to do this without a calculator, but talking and thinking at the same time is hard. It's 10 to the minus 17 newtons. And then the last thing is to figure out what direction it's going, right? Well, the electric field is pointing downward, but that is the direction the force would be on a positive test charge. The electron, of course, is a negative charge, so the force is going to be upward on an electron.